everyone, this is Matteo Matteucci from Politecnico di Milano, and this is the third lecture on neural architecture search. Today we are going to look at more advanced model on neural architecture search with respect to the PNAS and NetNAS architectures that we've seen in the previous lecture. So, what is the difference between modern architectures and the classical progressive architectures? Well, usually classical architecture were performing a search plus evaluation process, and this was an iterative process, very costly iterative process. And each time a new architecture was proposed, there was the need for retraining the architecture from scratch. Now, one-shot architectures, one-shot neural architecture system are reusing the weights at each iteration. So instead of training a cell, evaluating this cell, generating a new cell, evaluating this new cell, and throwing away all the results, what they do, especially one-shot neural architecture search, they combining the learning of the architecture with the learning of the parameters. And they treat each architecture as a subgraph or of a bigger supergraph, which they share the parameter with. The bigger subgraph is called supergraph. So the idea is that the search space with all these architecture that we see in the picture is just a subset of a bigger model. And each time we decide to extract a piece of this bigger model and to train a piece of this bigger model and to deploy a piece of this bigger model. By doing this, every time we train a piece of this model, we contribute to the training of the bigger model, and we can reuse part of the work for the next step. In particular, when this big model is trained, it can be used to evaluate any subset of it. So it means that we just need to train a big model and then hide pieces of this model to test different architecture. So the idea is that instead of training a lot of small network, let's train a big network and let's generate the small network as subpart of this big model. One of the first examples that was proposing this idea was called DARTS. DARTS stands for Differentiable Architecture Search. It allows to train the architecture parameters and the weights at the same time by gradient descent. And to do that, it introduces a continuous relaxation and a softmax operator on each possible path of the supergraph. So you can imagine that a cell, in this case, is represented by a directed acyclic graph with a topologically ordered sequence of nodes. Each node has some sort of representation to be learned, and each edge between these nodes is associated with an operation that transforms the input in the output. Now, DARTS relaxes the categorical choices of which operation has to be performed with a softmax, so a classification, over all possible operations. So the architecture search becomes an optimization problem where you have to learn this softmax over all the operations. So we can think about training as a B-level optimization. We want to find the best architecture, the best set of operation, such that we get the best performance at training time. So what we do, we optimize the weights, Once we have optimized the weights, we select the operators and then we iterate. Let's look at it with a picture. So let's assume we have this network and we would like to combine nodes 0, 1, 2, 3. At the beginning, we connect all the nodes together. What we have to learn is which one between the red, green, and blue step has to be selected in the final architecture. The problem is then modeled by a softmax operator which choose between the red, green, blue path at each time. And what we do, we learn this classifier. Once we have learned this classifier, we train the network. And once we have trained the network, we improve the classifier until the entire model converge to a single architecture, like the one on the right. What is the advantage of this model? Well, the advantage of this model is that you replace the cell-based approach by this super network. You don't have to perform some iterative search strategy. You can just learn the subnetwork by gradient descent. And by doing this, you don't have to retrain at each time a new network. You can reuse the weights that you have just trained. So the entire search strategy is replaced by stochastic gradient descent. You see how this has an impressive impact on the search cost. An algorithm that at the best was requiring a few hundred days of GPU now requires 4 days of GPUs. And it's also able to reduce the error on real dataset. This is the first work that was proposed in the idea of having a supernet learned once and then customized and then refined by gradient descent. Another algorithm that does the same is called once for all. And as the name suggests, it trains one network once and for all and then specializes this network for different devices. Indeed, what we would like to have is the possibility of training a big network and then specialized for cloud computing, for mobile AI, and maybe for tiny machine learning on, let's say, accelerated IoT devices. The idea is that obtained by architecture decoupling. Instead of optimizing both the architecture and the weights, as for darts, the once and for all separates the process in two. It first trains a large neural network, which we call supernetwork, which includes all possible subnetwork. This was done in an implicit way by darts, but it was at the same time also selecting the subnetworks during training. These subnetworks are derived after the supernetwork is trained by selecting subpath based on hardware constraint, based on requirements on the latency. So the difference between the darts approach, which also learn the optimized structure, with the once and for all, we divide the supernetwork training and the specialization of this subnetwork based on hardware constrained devices. This idea of learning one and then customize uses different tools, different mechanisms. One of these is called progressive shrinking. So this strategy, it allows to select excellent starting point for the subnetwork extraction, but also tries to concentrate the computational load into an end-to-end training process. So The algorithm starts by defining the maximal network, which includes all possible parameters to the maximum value. And then during training, the progressive shrinkings try to reduce the model and fine-tune both large subnets before getting the once and for all network. The progressive shrinking is organized in 4 elastic steps. Each of them includes different phases. The first step is elastic resolution. So while learning the SuperNet, progressive shrinking tries different size of the input image. The second step is called elastic kernel size. While learning the SuperNet, the progressive shrinking tries to reduce the maximum kernel size for convolutional operators across the entire network. It can use these 7x7, 5x5, 3x3 operators. Another step which is introduced by the progressive shrinking is the elastic depth, which tries to progressively decrease the minimum depth achievable for subnetwork. It is a sort of early exit. And finally, the fourth step is called elastic width. It tries to reduce the number of filters available for each convolutional layer. So you see that while learning the one and for all architecture, by means of the progressive shrinkings, we try also to simplify the complexity of the architecture. Now, what is nice of this is that once we have learned these big networks, these super networks, it's possible to extract subnetworks based on the requirement from the hardware that will be used to execute this network. If you remember, we can have different constraints either on accuracy or on the computational effort of this network. We have introduced this picture in a way simplified manner a couple of lectures ago. Now that once for all idea has been introduced, it is possible to design all the networks that we want by specializing the super network based on hardware constraint. This makes the super network training and the search strategy of once and for all more efficient and more effective than darts. For the search cost, we have a longer time for training the super network, but then the training of the specialized hardware takes 1.5 days, which is way faster than any neural architecture search done before. Another approach, which is very similar, well, actually, it builds on the one and for all framework, is called neural architecture transfer. The idea of neural architecture transfer is to transform a pre-trained generic supernetwork into a task-specific supernetwork, very similar to what one and for all does to specialize the supernet on constrained device. Neural architecture search selectively fine-tunes only those parameters of the supernetworks that correspond to subnetworks whose structure can be directly sampled from the current front distribution. Neural architecture transfer uses a multi-objective evolutionary strategy to extract out of the supernet the architectures of interest. The result is an improved performance on testing dataset. Neural architecture search uses the same techniques of one and for all. It requires a longer time to specialize the network, but it can achieve lower errors on average. With this, I'm closing the excursus on neural architecture search algorithm, and the lectures on narrow architecture search provided by the AI-SPRINT project.